A linear equation in three unknowns x, y, and z has the form ax plus by plus cz equals d, where a, b, c, and d are given real numbers, and x, y, and z are unknowns or variables. Now we're going to be interested in triples of numbers x, y, and z that satisfy these equations. So here is an example of a linear equation in three unknowns. Here is a triple of numbers that satisfies this equation. If we plug 1 in for x, 0 in for y, and minus 7 in for z, we'll end up getting 2 minus 0 plus 7 equals 9. We can think of this triple of numbers as a point in 3D space. This is how 3D space is usually represented in two dimensions. We have three axes, an x, y, and z axis. This here is the positive x-axis, this is the positive y-axis, and this is the positive z-axis. To see the negative x-axis, it extends behind the screen. The negative y-axis extends in this direction, and the negative z-axis extends downwards. And you could imagine plotting the point 1, 0, minus 7. You would go to plus 1 on the x-axis, you would go to 0 on the y-axis, and then to minus 7 on the z-axis, and you'd have a point somewhere out here, which I can't show very well, of course. Now geometrically, 2x minus 3y minus z equals 9 is a plane in 3D space. So we could imagine some plane in 3D space, but it has to contain this point here. Now, plane is a flat surface that extends indefinitely in all directions. Now, I've no idea where this plane lies in 3D space, and it's certainly far from easy to try to represent this graphically. If we have three linear equations and three unknowns, then we are talking about three planes. If all three planes intersect at a point, then we have a triple of numbers, or a solution that will satisfy all three equations simultaneously. Now this particular system has such a solution. So you could imagine drawing in a second plane. The second plane would intersect the first plane along a line. It might be this line here. Then you might imagine drawing in the third plane, which represents the third equation, and that might cut the other two planes something at some other angle. And this third plane would cut this line at some point, and that point, that triple of numbers, whatever it is, I'll just write down x, y, z for now, because we're going to find it, would be a point that's on all three planes. So the equations that we will deal with have a unique solution. The equations will represent three planes that all intersect at a point. Of course, it would be possible to have three planes that are parallel to each other that don't intersect at a point. It could be possible that the three planes are not parallel but enclose a triangular region, and so on. Now we're only going to be dealing with the case of three planes that intersect at a point. So in other words, two planes will intersect along a line, and that line will cut the third plane at one point. So to find that solution, or that point, what we do is we combine equations in such a way that we eliminate either x, y, or z. The easiest thing to do with these three equations is to take the second equation and add it onto the third equation. That way we can eliminate z, and we'll get an equation in x and y. Then what we will have to do is take a different pair of these three equations and eliminate z again. So that'll give us a second equation in x and y. We will have two equations in x and y, and we can solve between those two equations to find x and y. Once we've found x and y, we plug that pair of numbers x and y into one of these equations and find z. So I will start by adding these two equations together. When I add these two equations together, the z's cancel out. So we're allowed to add an equation to another equation, because we're just adding the same thing to both sides of one of these equations. You could think of it as adding the left-hand side of this top equation to the left-hand side of the bottom of equation is the same as adding 2 onto 9. And since x minus y plus z is equal to 2, we're just adding the same thing onto both sides of this bottom equation. So we get something that's valid. So this is a valid equation, but it doesn't contain z. So now we need to get another equation in x and y. So we need to pick a different pair of equations. So I could take the top equation and the bottom equation. They're convenient because I only have to add the top one onto the bottom one to eliminate z. So I don't have to do any multiplying. I don't have to do any adjusting. So this is the top equation, this is the bottom equation. Add them together, get 5x minus 2y equals 0 plus 9 is 9. Now, I have two equations and two unknowns, x and y. I solve between them to find out what x and y are. That will give us the x and y values of the point of intersection of the three planes. So, in order to solve these equations, I could eliminate y. So I leave this equation as it is, that's just this one here. And I multiply the second equation by minus 2 in order to cancel y. So we've minus 2 by 5 is minus 10x. Minus 2 by minus 2y is plus 4y. Minus 2 by 9 is minus 18. So we've plus 3 minus 10, that's minus 7x. These cancel out. We've 11 minus 18, which is minus 7. So that leads to a nice integer value for x. X equals 1. So knowing that x equals 1, we can plug it into one of these two equations to find y. So I'll take this equation here. So I'll write this equation down, replacing x with 1. So that leads us to minus 2y equals 9 minus 5, which is 4. Which means that y equals minus 2. Now the last step is to plug these two numbers into one of the three equations. Doesn't matter which one. And find z. So I'll use this one here, it's a little bit easier. So x is 1, y is minus 2, so we've 1 minus minus 2, or 1 plus 2, plus z equals 2. You can cancel these out, so we end up getting z equals minus 1. So now we know that the three planes intersect at the point with coordinates 1, minus 2, minus 1. Now, as a check, I'm going to plug this triple of numbers into the top equation. So the top equation is 3x. So I'm going to plug 1 in for x, plus y, plus z, and this should all work out to 0. So this is 3 minus 2 minus 1, which is 3 minus 3, which is indeed 0. And it should also work for the other two equations. Here is another example. Now, these two equations are equations of planes, but this equation up here is the equation of a line. It has only got two unknowns, x and y. So we're going to be finding the intersection of this line and these two planes. The two planes will cross on a line, and then that line will actually cross this line. So there is a solution to this system. So we eliminate z between these two equations. We multiply this equation by 4 to get 4x plus 4y plus 4z equals 0. 4 times 0 is 0. And I've just copied down this equation here. If we add these two equations together, we can eliminate z. So we get 7x plus 6y equals 9. And then we solve between this equation and 2x plus 3y equals 0. Now here I'm showing the solution between the equation we got by eliminating z from these two and the top equation, 2x plus 3y equals 0. So we have two equations and two unknowns. If you multiply the second equation by minus 2, we get minus 4x minus 6y equals 0. Add it to the top equation, so y will cancel out. 7 minus 4 is 3, 9 plus 0 is 0, so we get x equals 3. Plug this value of 3 into one of these. I've plugged it into the second equation, So we get 6 plus 3y equals 0, 3y equals minus 6, y equals minus 2. Then you pick one of these two equations that has three unknowns in it. I'm choosing this one. And we plug in these values for x and y. 3 plus minus 2 plus z equals 0. So 1 plus z equals 0, which means that z equals minus 1. So we found a triple of numbers that satisfies all three equations simultaneously. That triple is 3, minus 2, minus 1. This is a point that lies on this line, on the line and on both of these planes. Well, actually, come to think of it, this point here doesn't lie on this line, because if it has to lie in this line, then z would have to be 0. Z isn't 0, but it does satisfy the equation of the line. If we plug 3 in for x and minus 2 in for y, this will indeed work out to 0. But if we're talking geometrically, z would really have to be 0, but we don't really need to know that for our purposes. We just need to be able to solve between them. We don't have to know what's going on geometrically.